With this video, we begin our mini unit on Chapter 16, which is entitled Solubility and Complex Ion Equilibria. I'll let you know right off the bat, we are not going to deal with complex ion equilibria, even though it's interesting, it's not part of this course. So, let's focus on solubility. In Chapter 16.1, we're going to talk about solubility equilibria and the solubility product. So, what does the word soluble mean? Well, pretty obviously, if something is soluble, that means it is capable of dissolving to form a solution. And by the way, in this chapter, we're only dealing with ionic compounds dissolving in water. So what does insoluble mean? Well, pretty obviously, not soluble. Now, this is important. We talked about this in our first year of chemistry, and let's reiterate. What does an ionic compound do when it dissolves in water? It dissociates, which means it separates into aqueous cations and anions. And do you think any ionic compounds are actually insoluble? Well, this kind of points out one of the lies I told you in the first year of chemistry. When we talked about solubility of compounds, we kind of put them in two separate groups. Either it's soluble or it's insoluble. That really is a dramatic oversimplification. In fact, there aren't any compounds that are truly insoluble, but many are what we call slightly soluble. Now, dissolution and dissociation of an ionic compound is an equilibrium process, like we've been talking about for a long time now. So if I were to write an equation to represent the dissolution and dissociation of this hypothetical ionic compound, M sub A x sub B, as a solid, I would form M B plus cations, and I'd form A of them, which are aqueous, and I would form X A minus anions, of them, which are also aqueous. So I write an equation to show the ionic compound dissolving and dissociating into its cations and anions. Now, I can write an equilibrium expression for this, in which I simply include the concentrations of the products, in this case, the B plus cations, raised to the power of its stoichiometric coefficient A, times the concentration of the X A minus anions, raised to the power of its stoichiometric coefficient B, and we call this equilibrium constant Ksp. Sp stands for solubility product. It is a special equilibrium constant that governs the dissolution and dissociation of a slightly soluble ionic compound. Now, you will notice that in this equilibrium expression, it's all in one line. There is nothing in the denominator. Why not? Well, because my reactant is a solid, and we do not include solids and pure liquids in equilibrium expressions. So don't make the mistake of putting that concentration in the denominator. Ksp expressions do not have denominators. So here's a table that has lots and lots of Ksp values, and you can see, kind of, that they range dramatically. Barium hydroxide has a Ksp of 5.0 times 10 to the negative third, which means it's reasonably soluble, whereas mercury 2 sulfide has a Ksp value of 1.6 times 10 to the negative 54th. What does that even mean, 10 to the negative 54th? Well, we can talk about that in class, but as you can see, huge variation in magnitudes of Ksp values. So, here are the types of problems you're going to see. First of all, calculate Ksp for a slightly soluble ionic compound, given the solubility of the compound in moles per liter. Now, let's make sure we understand clearly what the term solubility means. Solubility is defined as the concentration of the ionic compound in moles per liter in a saturated solution. And a saturated solution, you'll recall, is one that has achieved solution equilibrium. So, for example, if I were to write an equation for the dissolution and dissociation of this hypothetical ionic compound, M plus aqueous plus X minus aqueous, when I have achieved solution equilibrium, I have the solid undissolved ionic compound at the bottom of my beaker, and I have dissolved as much of the ionic compound as I possibly can at that temperature. And it is not true that nothing is happening. When I have achieved solution equilibrium, I still have the ionic compound dissolving and dissociating to form the aqueous cations, but I have the aqueous cations and anions reprecipitating to form the solid at the same rate. So the solubility, which is a number that has units of moles per liter, is the concentration of that ionic compound, Mx, dissolved in solution. So, first skill, given the solubility, calculate Ksp. Second skill, first skill is calculate KSP given the solubility. Second skill is the reverse, calculate the solubility given KSP. Next, we will use KSP values to compare the relative solubilities of different ionic compounds. And I'll ask the hypothetical question, does the smaller value of KSP always mean that that one is less soluble? Well, I wouldn't be asking the question if the answer is yes. The answer is clearly no, and you will see examples of this shortly. And then finally, calculate the solubility of a salt in the presence of a common ion. That was second to finally. Really finally is predict the qualitative effect of pH on solubility. That is, for what categories of ionic compounds will the solubility depend upon the pH of the solution, and will the compound be more or less soluble as we increase or decrease the pH. That's purely qualitative. So let's begin. For each of the following ionic compounds, write a balanced equation to represent its dissolution, dissociation, and aqueous solution, and then write the corresponding KSP expression. In the interest of time, I'm not going to do all of these. I'll do one, and then you can pause the video and do the other ones for practice, and ask me in class if you have any questions. So, silver 1 chromate dissolves and dissociates to form silver 1 cations plus chromate anions. And to balance the equation, I need a coefficient of 2 before the silver 1 cations, and then to write the KSP expression. KSP is simply equal to the concentration of silver cations squared times the concentration of chromate anions. You can do the remaining ones for your own practice. Here, we're going to calculate the KSP values for each of the following, given its solubility. Well, in order to do that, and by the way, for the first one, lead-2 phosphate, the solubility is given as 6.2 times 10 to the negative 12 moles per liter. That means when I have achieved solution equilibrium, when I've dissolved and dissociated as much of the salt as I can, I will have 6.2 times 10 to the negative 12 moles of lead-2 phosphate for every liter of solution. Let's begin by writing out the equation for the dissolution and dissociation. Solid lead-2 phosphate dissolves and dissociates to form 3 moles of lead-2 plus 2 moles of phosphate. I'm going to write my KSP expression. KSP is the concentration of lead-2 plus cubed times the concentration of phosphate squared. Now, if S moles per liter of lead-2 phosphate dissolve and dissociate, what are the corresponding concentrations of lead-2 plus and phosphate? Well, obviously, I will have 3S moles per liter of lead-2 plus formed and 2S moles per liter of phosphate formed. Why? Simply because for every 1 mole of lead-2 phosphate that dissolves and dissociates, I get 2 moles of lead-2 plus, 3 moles of lead-2 plus and 2 moles of phosphate. Therefore, the concentrations of those ions are 3 and 2 times greater than the solubility, respectively. What that allows me to do then is simply to plug into the KSP expression in terms of the solubility. So this becomes 3S quantity squared, cubed, times 2S quantity squared, which is 27S cubed times 4S squared, or 108 times S to the 5th. So for this particular ionic compound, KSP is going to be the solubility raised to the power of 5 multiplied by 108. So let's do the calculation. 108 times 6.2 times 10 to the negative 12th. Again, that's the solubility that was given in the initial part of the problem, raised to the 5th problem, or 9.9 times 10 to the negative 54th. Ludicrously small number, but it is what it is. If you'd like to do another example, you can do the same for lithium carbonate. Now, let's go in the other direction. Suppose I give you the KSP value for the ionic compound and I want you to calculate the solubility. Well, we simply go in the opposite direction. Oh, let's do the second one here, lead-2 iodide, and you can do the first and the third on your own, if you feel like it. As always, let's begin by writing out a chemical equation to represent the dissolution and dissociation of the compound. So, lead-2 iodide dissolves and dissociates to form lead-2 plus cations plus 2 iodide anions. I will call the concentrations of lead 2 plus and iodide S and 2S respectively for solubility and twice the solubility. I'll write out the KSP expression. KSP is the concentration of lead 2 plus times the concentration of iodide squared. Let's plug in terms of S. That would be S times 2S quantity squared, which is 4S cubed. In the previous problem, you were given the solubility and you solved for KSP. In this type of problem, you're given KSP and you are solving for the solubility. Therefore, we simply rearrange algebraically to isolate S. S then is equal to KSP divided by 4 cube root. KSP is 1.4 times 10 to the negative 8 divided by 4 cube root, which gives me a value of 1.5 times 10 to the negative third moles per liter as my solubility. Now remember, that is the moles per liter of lead 2 iodide that dissolve and dissociate in solution. If I wanted to calculate the concentrations of the ions, I would need to use the appropriate mole ratios. Now, here I'm giving you two pairs of ionic compounds and their corresponding KSP values, and I'm asking you to determine which one has the lower solubility. In A, I'm given calcium fluoride and barium fluoride, and as you can see, their KSP values differ by a factor of about 1 million. Okay, barium fluoride is about 10 to the 6 times more soluble than calcium fluoride. Okay, so the question is, do we need to do any calculations to determine which is less soluble? Well, what you notice right off the bat is that because each of these two compounds is a group 2 metal fluoride, the dissolution and dissociation stoichiometry is the same. In each case, 1 mole of MF2 dissolves and dissociates to form 1 mole of M2 plus 2 moles of F minus, and the KSP expression has the same form, M2 plus times F minus squared, or as we said before, that's going to look like 4S cubed. So, if the KSP expression expressed in terms of the solubility S, if they're identical to each other, we can assume that the less soluble salt has the lower KSP value because the KSP expressions are the same. So we would conclude, and we would verify if we went to the trouble of doing the calculations, that calcium fluoride with the lower KSP value would be less soluble. But what about calcium phosphate versus iron 2 phosphate? Here we see their KSP values, and we see that one of them is 10 orders of magnitude smaller. So you might naively say, calcium phosphate must be the less soluble salt because its KSP is so much smaller than that of iron 2 phosphate. But let's look and see. So for calcium phosphate, dissolving and dissociating to form calcium cations plus phosphate anions. We will call the concentrations 3S and 2S. KSP is the calcium 2 plus concentration cubed times the phosphate concentration squared, or 3S cubed times 2S cubed. We've already seen this one before, which is 108 times S to the 5th. So S is going to be equal to KSP over 108 raised to the power of 1/5, or 1.3 times 10 to the negative 32nd over 108 raised to the power of 1/5, which is 1.6 times 10 to the negative 7th molar as my solubility. Small, but not ridiculously small. We could probably measure that in our laboratory. Now, let's look at iron 2 phosphate. For iron 2 phosphate, iron 3 phosphate, I misspoke. FePO4 in equilibrium with iron 3 plus aqueous plus PO4 3 minus aqueous. Here, the concentrations are just S. So, KSP is the iron 3 plus concentration times the phosphate concentration, or S squared equals 1.0 times 10 to the negative 22nd. So to solve for the solubility is simply equal to the square root of KSP, or the square root of 1.0 times 10 to the negative 22nd, or 1.0 times 10 to the negative 11th molar as my solubility, which is about 10,000 times smaller than the solubility of calcium phosphate. So we conclude that iron 3 phosphate is the less soluble salt. So take-home message, you cannot judge the relative solubilities of ionic compounds by comparing their KSP values unless the dissolution and dissociation stoichiometries are the same. If they're different, you have to do the calculations. Now, what we've seen so far are a couple of examples of dissolution and dissociation stoichiometries and the corresponding forms of the KSP expressions. Why not be systematic and consider all of the, not just likely, but possible likely because there are many more that we're not going to look at, the likely dissociation stoichiometries and the resulting forms of the KSP expressions. You will see that there really are only 4 different forms that you're going to see. So, let's consider the first one. MX dissolves and dissociates to form NN plus plus XN minus. The solubilities, concentrations are S and S. And I'll write my KSP expression. KSP is simply equal to X squared. So if the ions are produced in a 1-to-1 ratio, KSP is X squared. The next possibility would be one in which 3 ions are formed instead of 2. Either MX2 forms M2 plus 2X minus, or M2X dissolves and dissociates to form 2M plus X2 minus. Okay? You can easily see, so this is S, this is 2S, 2S, and S. You can see, without me really having to go into it, that the only possibilities here are going to be where you have KSP is equal to 4S cubed. What about if 4 ions are produced? I can think of 2 possible ways for that to happen, or 2 likely ways for that to happen. MX3 dissolves and dissociates to form M3 plus 3X minus, or M3X dissolves and dissociates to form 3M plus X3 minus. The corresponding solubilities would be S and 3S, or 3S and S. Either way, there are 4 moles of ions produced. So that means KSP is going to be equal to 27 S to the 4th. And then finally, if I have M2X3 in equilibrium with 2M3 plus 3X2 minus, or M3X2 in equilibrium with 3M2 plus 2X3 minus, or MX4 in equilibrium with M4 plus 4X minus. The corresponding solubilities are 2S, 3S, the corresponding concentrations, 3S, 2S, or 4S and S. In any of these cases, we have 5 ions being produced, so that means the form of the KSP expression will be, as we've seen a couple of times, KSP equals 108 times S to the 5th. So once again, when we write an expression to show how KSP depends upon the solubility, these are really the only likely ones that you will see. So let's move on. The common ion effect. We talked about this in terms of acid-base equilibria, and we saw in chapter 15 that in the presence of a common ion, namely a product of the ionization of a weak acid or weak base, that ionization is suppressed. The equilibrium is shifted towards the reactants. So the question in this section is, how would the solubility of a salt in a solution that already contains either the cation or the anion produced compared to that we observe in pure water? Well, we would predict that the ionic compound would be less soluble. That is, the pre-existing concentration of either the cation or the anion would shift the equilibrium to reactants, or towards the left, making the salt less soluble. And we would see that's true. Okay? So let's do an example of that. And here we're going to ask the question, what is the solubility of calcium phosphate in 0.20 molar sodium phosphate solution? So we're dissolving, dissociating it in a solution that already contains a substantial concentration of one of the products of the dissolution, namely the anion, the phosphate anion. So let's begin by writing an equation to represent the dissolution and dissociation of our ionic compound. We'll form 3 moles of calcium 2 plus 2 moles of the phosphate anion. We will call our equilibrium concentration of calcium 2 plus 3S. What's our equilibrium concentration of phosphate? Not 2S, but 2S plus the 0.20 moles per liter we started with. So I'm going to write the KSP expression and plug these in, because again, remember we're calculating the solubility S, and we have KSP equals the concentration of calcium 2 plus to the 3rd power times the concentration of phosphate to the 2nd power. This is 3S quantity cubed. The concentration of phosphate is 2S plus 0.20 molar concentration squared, which is 1.3 times 10 to the negative 22nd. Now, 0.20 is a fairly large initial concentration of phosphate, and because KSP is so small, we're going to make the simplifying approximation that 2S is so small as to be negligible in comparison with 0.20, so we will simply ignore it. So now, rearranging to solve for the solubility is KSP 1.3 times 10 to the negative 22nd divided by 27 times the solubility, the concentration of phosphate, 0.20 quantity squared, all taken to the 1/3 power, or 2.3 times 10 to the negative 11th molar as my solubility, which if you compare that to the solubility of calcium phosphate in pure water, you will see is substantially lower. So yes, the common ion effect applies just as importantly in equilibria involving the dissolution and dissociation of ionic compounds as it does in acid-base equilibria. Finally, how does the solubility of an ionic compound, and when does the solubility of an ionic compound depend upon pH? So the specific question is, how would the solubility of barium hydroxide in a basic solution, one with a pH greater than 7, that is with a higher concentration of hydroxide than pure water, compared to the solubility observed in pure water? Well, let's begin by writing out an equation to represent the dissolution and dissociation of barium hydroxide. It dissolves and dissociates to form barium 2 plus cations plus 2 hydroxide anions. Okay. Well, in pure water, we could easily calculate the concentrations of each species, but if it is a basic solution, then that means I have a pre-existing concentration of hydroxide, one of the ions produced in the ionization, so we would predict that it would be less soluble in a basic solution by Le Chatelier's principle. That is, the pre-existing concentration of hydroxide would shift the equilibrium toward the reactants. And shifting the equilibrium towards the reactants means that the barium hydroxide is less soluble. Now, what about in an acidic solution? How would the solubility of barium hydroxide in an acidic solution compare to that in neutral water? Well, you would predict correctly that it would be more soluble. Remember, an acidic solution is one that has a higher concentration of hydrogen ions than neutral water, okay? And we can actually show this by writing a chemical equation, okay? Barium hydroxide would react with the excess hydrogen ions present in the acidic solution to form liquid water. Oh, what the heck? Let's just assume that all the hydroxides are going to react. So we'll react with 2 moles of H plus to form 2 moles of liquid water plus barium cations in aqueous solution. This obviously would cause barium hydroxide to be more soluble. Now, does this only work with hydroxide anions? Well, no, as you would predict, if the anion has any tendency to accept a proton at all, like hydroxide really does, then the same process will occur. So we can generalize this by saying if the anion in the ionic compound is the conjugate base of a weak acid, then the salt will be more soluble at low pH because the anion will be protonated, driving the equilibrium towards the products. Protonated simply means H plus is added to it to form the conjugate acid of whatever that anion is. So if I ask you, will an ionic compound be more soluble at low pH, then you're simply saying, okay, is the anion the conjugate base of a weak acid? If it is, it has a high affinity for the hydrogen ion, and therefore it will be protonated, making the ionic compound more soluble. So on our final page, I give you a series of ionic compounds, and I ask for which salt in each of the following groups will the solubility depend upon pH. For each one whose solubility does depend on pH, will its solubility increase or decrease with decreasing pH? Remember, decreasing pH means increasing concentration of hydrogen ion, or more acidic, and write an equation to show why. We'll do the first one together. You can consider the other ones on your own time. And notice that there's a fourth one down here. So, in the first series of problems, we have silver 1 fluoride, silver 1 chloride, silver 1 bromide. And the question you're asking yourself is, well, is the anion of any of these compounds the conjugate base of a weak acid? Because if it is, it will have a high affinity for a proton. And in fact, you see that whereas chloride and bromide are the conjugate bases of strong acids and therefore not basic at all, fluoride is the conjugate base of the weak acid, hydrofluoric acid. Therefore, it will have a tendency to be protonated. So therefore, we would predict that silver 1 fluoride's solubility will depend upon pH. We would predict that it would be more soluble at, sorry, let me write this more cleanly. It would be more soluble at low pH, and the equation to show that would simply be solid silver 1 fluoride reacting with hydrogen ions to form the conjugate acid, hydrofluoric acid, plus the silver 1 cation aqueous. Okay, in the next video we will talk about precipitation.